Good news. That won't always be the case, so when it happens, you kind of enjoy the process a little bit. We know that we're dealing with, you don't need a precise graph, but you know that you're dealing with an upward-facing parabola and a linear function with a positive slope. So it's going to have a bounded region that's going to look probably something like this. Right? So what I'm looking for would be the intersection between the line and the parabola. All right, so I need these 2 points in terms of x. Then I'll pretty much have my integral, and then we'll be good to go from there. All right, so a little bit of algebra. X squared plus 2x minus 3 has to be equal to 4x plus 45. And we have x squared minus 2x minus 48. And so 6 and 8, I think. So x plus 6, x minus 8. And so we get our roots of x equals -6 and positive 8. All right, so in terms of x, obviously, because x equals, but we could have solved for the y values and changed our perspective, but you don't do that unless you have cause to do that. Right? You'll see in the next problem that we have to integrate with respect to y. That's a case where you're told to do it. There's some cases where you might choose to do it. Right? Here, it just makes sense to keep going in terms of x. So we have our bounds. Right? So this is starting at -6 and ending at 8. We know what the actual dominant, non-dominant relationship is, so we can subtract in the appropriate order, and in doing so we can kind of avoid the need for absolute values. If you weren't sure about dominance, or you thought maybe there would be a change in dominance over the interval, then you would include the absolute values, but not the case here. All right, so on the interval of -6 to 8, we have the linear function 4x plus 45. 45, minus x squared plus 2x minus 3 dx. All right, so we clean it up. We're looking at -x squared. We're going to have, looks like a plus 2x, and then plus 48 dx on the interval of -6 to 8. All right, so we have to integrate. So reverse power rule, not too bad. We're looking at -1/3 x cubed plus x squared plus 48x over that interval. Little calculation ahead of us. And then we're going to subtract from that -1/3 -6 cubed plus -6 squared plus 48 times -6. All right, the numbers are a little on the large side, but you know, they're not outrageous. So you're looking at values that, you know, they could conceivably end up on the non-calculator part. So that's why I'm doing it out like this. So 8 cubed, that's probably the beefy part of this. 8 times 8 is 64. If you want to multiply by 8, I mean, an easy way to do it would be to just double the number 3 times. right? So you want to look for little shortcuts like that. So 64 doubled one time is 128, and 256, and 512. So 8 to the third power would be 512. Right, so we have negative 512 over 3 plus 64 plus, so we'll double the 48 3 times. So 96 would be the first doubling, then 192, then 384. We could double check that. 8 times 40 would be 320, plus 64 would be 384. Right? So we can get it in one place. All right. We'll have to put all this together in a sec anyway, but the remaining values might be a little easier, because this one is 216, well, negative 216, but then it becomes positive 216 over 3, so that's 72. So negative 72. All right, well, that stinks. But again, we'll do some reorganization here a little bit, because I knew that this one was going to be 312. I can put these two together, but now they're not going to add to a nice number. They're going to subtract, though. All right, so 64 minus 36. So we're talking about, what, 28? Then I still have the 288. But that adds nicely with the, yeah, it gives us a 600. So we have the 628. So in a lot of ways, I guess that maybe the calculations are slightly easier than the way that the alternative method of not doing it the right way. All right, so the only issue is that, the common denominator part, 628 minus 512 over 3, not as fun, but doable, I guess. Another slightly different approach, instead of actually getting a common denominator, you could, this is not terrible to multiply by 3. You're really you're taking 1800 and you're multiplying 28 times 3 and just adding those two together. But you could change the 512 over 3 into a mixed number and then subtract it off. And then, because it's over 3, so it should be pretty easy to convert that back into a fraction. So it's really kind of dealer's choice at that point. All right, but I'll just do it the way I did it before, which is to get a common denominator. So 3. So I just need 8 times 3 is 24. So we're looking at 84. 1884 minus 512 over 3. So 1372 over 3. It looks like. And then we can see if we can simplify further, but at least we got a single value, and that's really all we were after here. So we can just call it at that point. Oh, look at all that. Yeah, so you can easily see the difference between a calculator problem and a non-calculator problem, because the calculator problem would have been done after the red step. None of this has to happen. You just type it right in and call it a day. But even an easy question, quote unquote easy question, could have some layers to it that you're not overly keen on. Right? So just something to be mindful of. Yeah, so arithmetic is still a thing, unfortunately. Or fortunately, depending on whether you like it. I don't mind it.
So the area of the shaded region, or the area of the bounded region is 1,372 over 3. What unit is that?
That would be square units. we just don't have any units in the context of the problem, so, but square feet, square miles, whatever. So in the next one, we have a natural log function. Now, when you deal with transcendental functions, those actually end up being kind of nicer when it comes to doing a problem out by hand, because the derivatives and antiderivatives work out nicer. That's number one. But number two is you can only go so far in the evaluation process, right? Because once you take, let's say, the natural log of 2, you're already in decimal form, right? So if it's a non-calculator problem, the expectation would be that you would leave it as the natural log of 2 and not actually go to decimal form. So you could, like I said, you can only go so far, which is generally a good thing in terms of the quantity of work, right? So what we need here is the region bounded by y equals the natural log of x, the axes, and y equals 3. So I'm just going to draw a quick sketch of that. Again, it doesn't have to be perfect, but it should have the important features of the graph. All right. So it should look something like that. All right, the natural log function is a forever increasing function. It just slows down in its rate of increase. Right? So you can say its acceleration is getting smaller and smaller as time goes on, if it's a time speed kind of thing. It has an x-intercept at 1. All right, and so this poses a little bit of a problem because we're going to have a little bit of a dominance issue here, right? That dominant function, y equals 3, applies throughout the interval, but the non-dominant function only starts when x is equal to 1. All right, so what I would need, or well, it would be handled in 2 possible ways. I would either need 2 separate integrals to handle this, broken up based off of that change in dominance, or one integral to address this component, and then some geometric component, right? So an area, like a rectangle.
Yeah, I'm a little bit confused about what you're talking about with dominance and why we need to do something.
When you're finding the area between curves, you're always subtracting dominant minus non-dominant, meaning the one that's on top subtracting from that the one that's on the bottom.
Right.
So here, from 0 to 1, the top function is y equals 3, but the bottom function is y equals 0. From here on, the top function is y equals 3. The bottom function is the curve. It changes over. So we have 2 different relationships that are at work here. All right? Yeah, sure. So depending on how you reason this out, you could kind of paint yourself into a corner. Right? So I'll show you three different ways to do part A. I'll start off with the most complicated way. All right. So the most complicated way is the way generally to be avoided, but sometimes it's your default. You would say, well, I don't know any other way to do it, so this is the way I'm going to do it. All right. So I have the line y equals 3. And again, the line y equals, I'll do it a different color, y equals the natural log of x. All right, we do have a point of intersect. All right, in terms of x, we don't have that yet, but I know y is equal to 3, so I could say that 3 equals the natural log of x, making x equal to the e to the 3rd power. All right, so that gives me a bound for this region, e to the 3rd power. So the actual coordinates for this point are e to the 3rd, comma, 3. So even the act of finding the intersection was a little bit easier than the polynomial case. All right, so I would set up an integral. This is the first approach. Set up an integral going from 0 to 1. Dominant function minus the non-dominant. So the dominant here would be y equals 3. The non-dominant would be y equals 0. So you would say 3 minus 0. And that's a dx. All right, because our infinitesimal rectangle is vertically organized to have a thickness with respect to x. All right. Now, for the other part, well, what I really need is, I need this area here. All right, so in order to find that, again, it's dominant minus non-dominant. So I'm going to add to this integral that I already have, I'm going to add the difference. And this is happening over 1 to e to the third. I'm going to add the difference between 3 and the non-dominant function y equals the ln of x. So ln of x dx. All right, so that's one approach. That would get us the answer. If we had to do it by hand, it would suck. Because unless you actually know the rule for the antiderivative of the natural log of x, you'd have to use integration by parts in order to come up with it. So, not fun. Right? So, second approach, a little bit more convenient, would be to say, well, I know that this first piece here is rectangular. I don't need an integral to figure that out. Right? Its base length is 1, its height is 3. Right? So I would just say 3 is the area for that first piece, plus, and then just do the rest of it exactly the same way. And by the way, if you reason this out, just consider the whole situation. Look at this entire region as being rectangular. You should be able to come up with the easiest way to do this, which would be to say, all right, well, why don't I figure out the area of the region that I don't want, which would be everything under the natural log curve here. All right, so on the interval of 1 to e to the third, so all the area that I don't want subtracted from the area of this entire rectangular region, which has a length of e to the third by 3. So I could say 3e to the third minus the area that I don't want, and that would give me a unique integral, or a set of integrals, or 3 unique sets of integrals, all giving us the same thing, all right? And again, you could already imagine the multiple choice question saying, which of the following integral is not appropriate for finding the area of the bounded region? And then these are 3 choices, and there's a 4th one in there that kind of looks like one of these 3, but isn't the answer. All right. So, but the one thing you should notice that's in common from one to the next, is that they all have that ln in it, which is a problem, because it means work. Right? We know how to find the antiderivative of the natural log of x, we just don't want to. All right, that's the key. All right? There are some problems where you're going to be given a type of function that you won't be able to find the antiderivative of. It's not a question of preference, it's just you will be incapable. All right, for those situations, you don't have a choice. But for these kind of situations, you should make the appropriate choice, and that is to say, well, let me take a look and see what's going on from the perspective of y. All right, because maybe things will be a little bit easier that way. So, same graph, kinda. All right. Now, in this case, I mean, I just cleaned up the graphic, just made it bare bones here. If you look at it carefully, you realize that the entire bounded region is adjacent to the y-axis, right? The entire bounded region here was not adjacent to the x-axis, right? There was that gap separating the x-axis from some of the bounded area, right, vertically. Horizontally, there is no gap between your axis and the bounded region. That's the key indicator that the best way to attack this problem is from the perspective of y, right? If I were to draw an arbitrary rectangle anywhere in this region, I could get from the axis to the function passing through the bounded area without any interruption, right? That's the name of the game. So that tells me that I'm looking for a dy, all right? So my function here is y equals a natural log of x, but let's solve for x in terms of y. X would be equal to what? E to the y, all right? So integrate e to the y dy over the interval, well, it starts here and ends here, over the interval of 0 to 3. And that's really all you need.
Why is it 0 to 3 and then 0 to -3 to the
So we're going, when we're doing it from the y perspective, we're going bottom to top.
Oh.
All right, so antiderivative of e to the y is e to the y over the interval of 0 to 3, which would be e to the third minus e to the 0th, which would be e to the third minus 1. And that is way simpler than any of these three possibilities. Like way simpler. And that's really what you want to kind of wrap your brain around. If that's the only thing that stands in the way between people, just kind of going through the motions, writing down what they suppose is probably the correct integral, punching stuff in the calculator and hoping for the best, and actually truly understanding this. Just trying to really develop the understanding of the perspective component. Like, why is it important to know it both ways? All right. Why is it not a choice? Why is it sometimes just a necessity? All right. Yeah, and that's really the name of the game. So, what I think would probably be the best move at this point would be to let you try number 3 on your own, because I think I honestly have no idea what time the period ends. 33, 32? Okay. So, yeah, so that's enough time for you to tackle this problem, because obviously if you didn't get number 2, you didn't get number 3. So.